Hello everyone. My name is Zaheer Khan and I'm Associate Professor at the University of Oulu. Today I will talk about radar sensing system on chip modules with applications in 6G communications and advanced driver assisted systems. There's always a mixture of evolution and revolution with any next generation of wireless cellular technologies. While from the first generation to the fourth generation of cellular technologies, new applications were added. 5G has been characterized by providing better mobile internet, which brought operators more efficiency and opened up possibilities in enterprise applications. Back in 1980s, starting with supporting 10 kilobits per second data rates in the first generation, we now see that the current 5G wireless cellular standard can support 10 gigabits per second, and the 6G networks are expected to see further tenfold increase in data rates. Modern telecommunication networks use advanced multiple input, multiple output MIMO techniques to create spatially separated paths. Starting with 2 by 2 MIMO support in the earlier generations, the 5G networks can support massive MIMO streams, adding to complexity in cellular baseband processing. Researchers are aiming to make 6G more than only somewhat better mobile internet. Providing support for new applications will be something which will make 6G different from 5G. Enabling sensing capabilities in 6G networks is one way to achieve that. In 6G research, there is growing interest to utilize radio waves for purposes other than communication. Radar like sensing capabilities could be used to enhance the performance of the network itself by providing input for network link optimization. For example, via sensing, we would be able to detect objects that temporarily obstruct the direct propagation path between a transmission node and a device. This input, in turn, can be used to improve beamforming algorithms. Not only in communication networks, but radar sensing is finding new applications in automotives as well. In advanced driver assisted systems and autonomous driving systems, automotive radar sensors serve as the eyes and ears along with camera, LiDAR, and ultrasonic sensors. A radar is a detection and ranging sensor that uses radio waves to measure the positions and trajectories of objects. It works by transmitting radio waves in the direction of interest. They bounce off objects in the vicinity and return as echoes to the sensor. The sensor then compares the characteristics of these reflected waves against the transmitted waves to infer the positions and movement of the objects. Enhanced MIMO capabilities with several TXR exchanges can be used to create new sophisticated high-performance radars called imaging or 4D imaging radars. Imaging radars provide a radio photo of the scenes that's closer to cameras. This approach offers the advantage of not only measuring the angle of arrival, but also enabling the separation of objects' resolution based on their angles. Increasingly complex MIMO communication data processing systems in 6G along with MIMO radar sensing data processing under challenging scenarios requires sophisticated system-on-chip data processing modules. A system on chip is an integrated circuit that consists of multiple electrical components on a single platform. The CPUs, DSP processors, hardware accelerators, and GPUs are some of the available wireless data processing options, integrated into an heterogeneous multiprocessing element SoC platform. Traditionally, wireless data processing can be done using CPUs, FPGA, ASICs, or nowadays even with GPUs. Each option has its own merits and limitations from data processing needs, such as performance, power, programmability, and time to market. One can see from the figure that while ASICs provide best performance and power consumption, but they lack flexibility and take longer time to market. GPUs and CPUs can be very flexible, but their performance and power consumption scores low when compared with an ASIC or an FPGA design. Driven by additional 6G sensing data processing needs, the complexity of the 6G SoC system will increase. As sensing data processing requires new data processing features such as 2-dimensional and 3-dimensional FFT plus customized detector, the number of complex subsystems on the entire cellular SoC system can increase. This can in turn means requiring increasing the number of processing elements on the chip. On the one hand, applications drive the increase in demand for processing elements. On the other hand, if these processing elements are of lower cost and more flexible design, it will be easier to handle such an increase in complexity. Historically, increase in data processing needs have been addressed in a variety of ways. One way has been by using multiple heterogeneous processing elements on a single chip to pack more stuff in less area. Process nodes are now hitting limits due to the end of Moore's law. This means new chip designs are needed. Use of advanced chiplets-based SoCs is now driving the future of 6G sensing and AI ML applications. In this approach, divide the large complex SoC into smaller chiplets, link them together to build a complete system for specific applications. The figure illustrates a high-level example of a monolithic versus chiplet-driven approach for incorporating sensing data processing capabilities in a cellular data processing SoC. One important question to answer is that should we have a separate sensing computation module chiplet, or should we incorporate sensing processing modules within the existing data processing chiplets? Next, we look at what a sensing data processing module in a SoC incorporating heterogeneous processing elements can be comprised of. A radar sensor is a full duplex system which transmits signals in bursts containing multiple complex samples, and it simultaneously listens to the reflected echoes. There can be multiple chains to process for a MIMO sensor, which depends on the number of transmit-receive elements. From data processing point of view, this type of sensor module can be divided into programmable control subsystem and DSP subsystem. Control subsystem can be comprised of an embedded processor used to control communication between the device and external equipments. Spare MIPS on this processor can be used to run late-stage algorithms like tracking and fusion. The DSP system, which does most of the computation tasks, can be comprised of hardware accelerators and DSP processor as shown in the figure. The high-level DSP processing chains is illustrated in the figure, and one can see that multiple dimension FFTs, interference mitigation, and detection algorithms dominate the data processing, whereas one also needs to take into account memory transfers using direct memory access to bring data to and from the on-chip memory. Using customized FFT hardware accelerator repeatedly, a significant portion of the custom compute load on the DSP processor could be relieved, and DSP processor can be used to do interference mitigation and detection tasks only. Other architecture approach can be to use multiple high-end DSP processors to do all the processing using the programmable processors. However, an architect needs to carefully evaluate the performance, power, and area trade-offs in the use of only programmable DSP processing versus a mix of hardware accelerator and programmable DSP processing. Unlike communication systems where transmissions are driven by user needs, sensor transmissions can be controlled and predetermined according to the detection and ranging needs. This is one important feature which can be exploited to minimize the number of processing modules for the sensor chip. By reusing the IP processing modules, in such sensors, one can incorporate idle time for B bursts of samples to exploit IP reuse for multiple dimension FFT and detection processing. Depending on the application, this idle time is a SoC design parameter. Let's consider an example where such a sensor is needed to detect a drone or a vehicle. Drone and car typical average speeds are 100 km per hour. For a typical 20 microsecond burst periodic interval and with 64 such bursts before idle time, introducing a 50% idle time would mean time of 1.6 milliseconds. This corresponds to only 4 cm change in car or drone position, which is negligible for many range, velocity, and direction estimation applications. Now let's take a look at high-level processing and memory requirements. The figure shows B burst of n complex samples followed by 50% idle time. The range FFT is usually performed inline for each of the transmission bursts, where each burst contains n complex samples. This means that the range FFT is the most latency critical processing. The Doppler FFT operates across multiple bursts and can only be performed while all the range FFTs corresponding to all the bursts are available. Lastly, the angle FFTs are performed on the range Doppler, processed data across multiple receive antennas. Managing data flow in a SoC is a key architecture challenge. As direct memory access lets various SOC modules transfer data between themselves and memory without involving the processing cores, DMRs are important in ensuring data flows in sensing SOCs. A typical radar-driven sensing signal processing chain requires data transfer from the ADC buffer to the DSP local memory, L1 or cache. It also requires data transfer to and from the DSP and on-chip memory, or to and from the hardware accelerator and on-chip memory. These data transfers are primarily accomplished using the DMR module. It is important to orchestrate the various types of DMR transfers, such as contiguous and contiguous write, contiguous read, and transpose write. Understanding DMR transfer latencies is very important, as this will enable the stitching together of a data flow that has minimal overhead, and it will ensure that data flow is as non-intrusive as possible. Here is a high-level block diagram illustrating direct memory access enabling data flow between a hardware accelerator and on-chip memory as scenario 1. Whereas in scenario 2, the DMR module enables data flow between a DSP processor and on-chip memory of the radar sensor. This data flow ensures that without significant overhead, the same processing element is reused for multiple dimension FFT processing for range, velocity, and angle estimations. We next present DMR transfer latencies for 128-bit with bus, where DMR clock rate is assumed to be 200 MHz. It can be seen that to transfer a single block of, let's say, 256 complex 16-bit samples, contiguous read and contiguous write will take 0.32 microseconds, whereas contiguous read and transpose write will take 4 times more time and hence 1.28 microseconds. Note that the sample size 256 is just an example, and in general the sample size can be 256 for FMCW waveform signals and much greater for OFDM signals used in cellular communications. As to perform second and third dimension FFTs on data, we need to store data in on-chip memory. Hence, it is also important for a SOC designer to understand the size requirements for the on-chip memory. For 16-bit Doppler processing case with multiple receive chains, the on-chip memory requirements can be calculated as a multiple of n complex samples into B bursts and R antenna chains. For example, for 256 complex samples and 64 surge bursts and 16 receiving antenna chains with 4 bytes per sample, we will need 1 megabyte of memory. For 2D and 3D FFT, it can require higher dynamic range for certain application cases, and in that case, the requirement of the memory can double to 2 kilobyte of memory. Moving towards the end of the talk, let's look at some benchmarking numbers comparing a low-cost 600 MHz clock DSP processor versus a low-cost 200 MHz clock hardware accelerator performance when they are utilized to perform FFT processing for the same sensor SOC. It can be seen from the table that the DSP processor takes 516 cycles for 128-point Doppler FFT and slightly less than double cycles for 256-point range FFT. It can be also seen that for the multiple receive chains, the cycle count is simply the multiple of the utilized number of received antenna chains. For the hardware accelerator case, it can be seen that the cycle count is almost 1/4 of the DSP cycle count. This increase in performance comes at the cost of programmability. Next, some more insights relating to the benchmarking numbers are presented. Let's say that each range FFT processing deadline is 26 microseconds. Assuming there are 64 such transmission bursts, then the second and third FFT processing is needed to be completed within the idle time period, which can be 26 into 64 microseconds. The benchmarking numbers for the SOC using the example DSP processor and the hardware accelerator, including the DMR transfer latency, indicates that the example sensor SOC can process around 12 to 16 receiving chains within the deadlines. Modern high-end DSP processors and hardware accelerators can have much higher clock rates. Very wide SIMD width and other architecture enhancement which allows them to increase the processing capabilities up to 8 to 12 fold more. This 8 to 12 fold performance increase enables the use of advanced imaging radars. To conclude this talk, while there is intense research activity for 6G networks to integrate radar sensing capabilities along with enhanced communications, much of the research focus has been up till now towards the algorithm design. This talk steers the research direction towards the SOC data processing relating intricacies that will eventually be needed for any of the sensing capabilities to be incorporated in 6G cellular networks. I thank all of you for listening to this talk.